Okay, so here's what we were doing last time. We were talking about cross-sections. What I like to call cross-sections, what the book likes to call traces. I just feel like the term cross-section is more relatable. And the big idea is that if you're trying to understand some surface, some, yet to be determined surface that is described by some equation, well, the idea is if you add another equation into the mix, which of course is another surface, and if this is a surface that you understand very comfortably, like a plane, nice and easy, right? Then the intersection of those two surfaces is going to be described by, well, the combination of those two equations, which is very often easy to understand. Two variables alone, for example, because notice we're eliminating z by setting it equal to a constant in effect, right? So this is easy to understand. That makes the cross-sections of the surface easy to identify, and that's a foot in the door to understanding the surface. Okay, so there's you can take this to great lengths. Here we took horizontal cross-sections. Here we took some vertical cross-sections. You can take vertical cross-sections the other way, right? And you can then try to piece together those cross-sections to figure out what the surface actually looks like. Good news about this plan, you can always take cross-sections. You can always set some variable equal to a constant, right? Bad news is you have a pretty significant art challenge in drawing what the cross-sections look like, which is, very often part of what it takes to visualize how to reassemble those cross-sections into a whole surface. So, it's, this is not the magic silver bullet technique. Right? Okay, let me show you what I think kind of is a kind of silver bullet-like. I'm going to start with an observation, a really cool observation, and that is, if you have an equation that involves, I'm going to say, for example, x's and y's only in this specific form as part of the expression x squared plus y squared, or square root of x squared plus y squared, or anything that you can make out of square root of x squared plus y squared. Hypothetically, let's suppose if, big if, this will not always be the case, but if your equation has that feature that, hey, check it out, weirdly, x and y only show up in that special form, then I claim that your surface is rotationally symmetric around the z-axis, and that's a huge amount of information. Here's the argument as to why that's true. Let's suppose that our equation has this feature. X and y appear only as part of this special form. This is the one that very often kind of tends to show up. Well, consider 2 points that are rotations of each other. Here's one point. And now let's imagine drawing a little arm that goes over to the z-axis and then rotating it, around. Like the z-axis is a hinge. Thus giving us now another point. Well, I've got 2 points, right? And sure, they have different coordinates. They're different points after all. So they have different x coordinates, different y coordinates. Oh, it's not immediately clear. When you have 2 points with different coordinates, obviously, how they're going to plug into an equation, well, who knows? Maybe one will work and the other one won't, or who knows what, right? But in this case, even though x and y are different, notice x squared plus y squared is the same for both. Likewise, the square root of x squared plus y squared is the same for both. Why? Well, because these distances are the same for both, because that's how we made those points. Right? Also, because of how we made those points, we were rotating around the z-axis, those 2 points are in the same plane, and so they have the same z coordinate as well. Different coordinates, but same z, same square root of x squared plus y squared. And so, by assumption, now keep in mind, our equation that we're looking at involves these variables that, those variables are different. Okay, sure. But only in this form where these 2 points agree. And then, of course, there's going to be z's in the equation, but these 2 points they agree on z as well. And so what's going to happen then is if any one of these points satisfies the equation, the other one does too. And geometrically what that means is that if this point is on the surface, then that point also on the surface. Or said differently, if this point is not on the surface, then that point is not on the surface. And unavoidably, the conclusion then is that this surface is going to be rotationally symmetric around the z-axis. Okay, now, you could call that just kind of, a little geometric curiosity. Let me show you how powerful this observation is. We're going to revisit this equation. Now, we went to great lengths on the previous page to try to understand what does this thing look like. I mean, taking cross-sections in different ways and having the artistic challenge of drawing those cross-sections and the artistic challenge of thinking about how do they glue together to form a surface. Check this out. This equation, x and y appear only as part of this special form, and so it's rotationally symmetric around the z-axis. There's that observation that we made above. Furthermore, I can easily take one cross-section in the plane x equals 0. There's the plane x equals 0, right? Oh, that one cross-section, if x is equal to 0, that term goes away. We just get z equals y squared. That's easily seen to be a parabola. So my surface is a rotationally symmetric surface whose cross-section in that plane is a parabola. Let me say that a little bit differently. My surface is what you get when you take this parabola and rotate it around the z-axis. And that's, I'm going to say clearly, a bowl. So we don't have to take a bazillion cross-sections. If you get so fortunate to notice that your surface is rotationally symmetric around an axis, take one cross-section, right? And then boom, done. Very powerful technique. I wish the book would sell up this technique more than it does, which is very little. I think this is really, really powerful. It's a big deal. So I encourage you to take advantage of this. Please do note that you have to document when you use this trick. You can't just say, this cross-section is that parabola, therefore paraboloid, right? You've got to observe the rotational symmetry, right? So make sure that it's clear what your reasoning is. I emphasize this is not a class about getting right answers. This is a class about making valid, mathematical reasoning. Your reasoning is what we're ultimately looking for. Okay. All right. I want to point out one other little detail before we do a few more examples of this technique, and that is that, remember I said, so you got to just take one cross-section. Be careful about one thing. If your symmetry is around the z-axis, and if you're going to look at just one cross-section, as I did here, what you need is for that cross-section, in rotating around that axis, to actually sweep out, sort of, if you will, everything. Right? And let me show you sort of what wouldn't work. Like if I were to, for whatever reason, I'm going to take the cross-section in the plane, maybe I don't want to do that. I want to take the cross-section in the plane z equals 0. Well, if you take the cross-section in the plane z equals 0, then you're looking at that one cross-section there. Rotating that around the z-axis just doesn't tell you the whole story. That does not address at all what's going on up here, because these points up here, you don't rotate into them from this plane z equals 0, right? So the way you get around this problem, simple rule, make sure that the plane that you look at, make sure that contains the axis of symmetry. You got to take a cross-section plane that contains the axis of symmetry. Fully contains it. Not enough to just intersect. The axis has to sit entirely inside of there. Okay, all right. So a couple more examples. Here's one. We already did this one. By the way, the name, this is called a paraboloid, again, because it's a rotation of a parabola. Here's a related kind of example. Let's look at this equation. Now, I want to emphasize this equation does not satisfy the rule on the previous page, right? X and Y do not appear strictly in the special form, right? Look at that. There's a stray X. Right? That's just not, you can't make X out of the square root of X squared plus Y squared. Right? So you cannot declare that this is rotationally symmetric around the z-axis. It isn't rotationally symmetric around the z-axis. However, do notice that there's an analogous thing happening over here with y's and z's. And I'm going to leave it as an exercise for you all to think through, a good practice problem to think through on your own. If y and z appear only in this special form, then the result is rotationally symmetric around the x-axis. Right now, it's kind of plausible from a moving letters around on the page point of view, but I want you all to think it through from this point of view. Think about how would you make the argument that such a surface, an equation, surface with such an equation must have this symmetry. What points? What are you rotating around? What are the lines? What are the distances? Think through the details. Anyway, what you'll conclude is that this is rotationally symmetric around the x-axis. Now again, all I have to do is think about a single cross-section. Cleverly chosen. I'm going to choose, it doesn't really matter. I'm going to choose the xy plane. Note that contains that axis of symmetry. If you want, you could choose instead the xz plane. Totally fine. That also contains the axis of symmetry, right? Just don't pick the yz plane. That doesn't make any sense, right? Okay, so let's do this one. That plane there, you'll notice, is described by easy equation. This plane is z equals 0. So let's take z equals 0 and toss that into there. And notice that our equation becomes x equals y squared. And thus an algebra 2 problem. And not hard to persuade yourself that x equals y squared is a parabola. It's a parabola that sort of opens up along the x-axis. Keep in mind, this parabola is what you get when you're looking in this plane. And so that tells you that the cross-section there is a parabola like that. Rotate, and out comes your... Now, you've got to visualize now, this is a geometric challenge, but what happens when you take this parabola, rotate it around the x-axis? Well, you're going to get this paraboloid thingy here. Yeah. Okay. Everybody see the reasoning there? Okay. All right. Okay. Here's one. Oh, here's a few more practice problems for you, by the way. Something good. Make sure you think those through. Make sure you're comfortable with how those would work. Here's another one. Let's look at this equation. Now, x and y appear only in the special form, so we know this is rotationally symmetric. Therefore, we know we only have to look in one plane, and then we could just say rotate around the z-axis. So, what plane do we want to pick? Okay, I'm going to pick this plane. Now, I could just as well have picked that plane. Doesn't matter. Take your pick. Doesn't matter. I'm going to do this one. This plane here has equation y equals 0. Take y equals 0, plug it into there. Our equation then becomes, let's see here, x squared minus z squared equals 1. And that is a hyperbola sitting inside, of course, this plane. Our surface then is what you get when you rotate that hyperbola around the z-axis. You got to think it through, think about the geometry, persuade yourself. But it gives you this... let's see here. I'm going to draw this thing, and it gives us this. I don't know what to call that. Corset, maybe, right? Anyway, whatever that is. It's called a hyperboloid. Okay. Now, there's a little detail on this one that I want to remind you of, something to think about. A lot of students have forgotten their Algebra 2. Honestly, this was always hard for me to remember, oh God, okay, so I know that's a hyperbola because I see the squares and there's a single minus sign. I know it's a hyperbola, but which way does it go? Shoot, does it go like this or does it go like that? Right? I mean, which way does it go? So how you remember your Algebra 2 is a personal choice. It's entirely up to you, right? I'll tell you how I remember it. And so I'm not a memorizer. I just don't believe in memorizing. I think that anything that you memorize, you're going to forget. It's a question of time, right? So I never actually memorized which way does it go. So, but here's my little trick for thinking it through. let's imagine what would happen if x were equal to 0. Let's see, I'm going to write this down over here in reference to this thing. I'm going to say x equals 0 question mark. Wait a second. If x were equal to 0, that would require that a negative of a square be positive 1. And that doesn't make any sense. There's no way that's ever going to happen. Right? So what we conclude from this is that x cannot equal to 0. Now inside of this plane, let me remind you, we're looking in this plane here. Inside of that plane, when I say x can never equal to 0, right, so I'm going to say no here. X cannot equal to 0. Well, here's what it would be when x is equal to 0. That means we're not allowed to touch that line. So which hyperbola is it? Is it this one? No problem. It doesn't touch the forbidden line there, right? But wait a second. Could it be this? No. It's not allowed to touch that forbidden line. Right? So there's no way that it could be this hyperbola. Violates sanity. Right? And so therefore it's got to be the other one. So this is how I keep that straight for whatever it's worth. I hope that helps. Anyway, otherwise, just make sure you get it right. Makes a dramatic difference in the answer, of course, if the hyperbola goes the other way, if you get the hyperbola going the wrong way. Okay. All right. Okay, so here's another one. Now, this one does not leap off the page very well. X and Y, you'll notice, do not appear in the proper form. They just don't. Right? X squared minus y squared. Close is not good enough in this situation, right? X squared minus y squared kind of looks like x squared plus y squared. Not good enough. It's got to be exactly, strictly following the rules. Just doesn't. But what you'll notice, if you think about it, is that you can rewrite this equation as instead x squared minus y squared plus z squared equals 1. And now notice that y and z appear only in the special form, and therefore this thing is rotationally symmetric around the x-axis. And then off you go, right? I mean, think about what the cross-section looks like. Which cross-section are you going to look at? Arbitrarily, maybe y equals 0. Plug that in, see what the equation you get, what hyperbola is that, make sure to get your hyperbola straight. Right? And then visual problem of rotating it. Do notice, I'm going to let you all go through those details. Do notice in this case, it happens to be that same hyperbola there. But here we're rotating around the x-axis, and so we don't get that corset-looking shape. Here we get what I like to call the staring contest. Right? It's like there's a little eyeball staring at another little eyeball. Right? So this is, now they also call this a hyperboloid, because it's still a rotation of a hyperbola, right? As was this one, also a hyperboloid. But notice that this hyperboloid, let me clean up my mess here. This hyperboloid is made up out of, well, a single sheet, we call it. There's not two separate chunks, it's just one chunk. Whereas this, the staring contest, has two separate sheets, right? This surface over here never touches this surface over here, so thus two sheets. Yeah? Everybody good? Okay. All right. This one's all a disappointment. By the way, this is a disappointment that you absolutely have to get used to. At a glance, you look at that, you see those squares, you think, oh gosh, a rotation, wouldn't it be nice to be able to make a rotation argument here? But I'm sorry, there is no rotation argument to be made. X and Y do not appear in that special form. There's that minus sign. It doesn't just disappear because we want it to. That is not part of the special form. X and Z, nope. Right? Z isn't squared. Y and Z, nope. Right? It's just too bad. There is no rotation argument to be made. In fact, this surface, no surprise, is not rotationally symmetric. So, this silver bullet method of making a rotation argument, it has this huge asterisk, which is it only applies if the algebra fits the very strict restrictive form. And, honestly, very often / usually it just doesn't. And so, it's a great technique sometimes. It's a tool in your toolbox. There's a lot of tools in a toolbox that are only useful in very special situations. Still very valuable tools. Okay, this one you have to make a cross-section argument, right? So we can start setting x equal to various constant values. Right, and start looking at the cross-sections in these planes. You can see when you set x equal to a constant value, whatever that constant is, you're roughly speaking going to end up with parabolas. And so you get surfaces that look kind of like, you get cross-sections that look kind of like that. And then think about it cross-sectioning the other way. Going the other way, if you're setting y equal to a constant, notice your paraboloids are upside down because of that, because of that minus sign there. Right? And think through the various details. I'm not going to go through the whole thing here, but it ends up being that this surface, they call it a hyperbolic paraboloid. I'll talk about why in a second, but I think the most relatable way to describe that is it's a Pringle. Right? I mean, by the way, this is the day that when I remember in advance, this is the perfect excuse for me to buy a can of Pringles, because then I can rationalize it as a visual aid for class, right? And then I eat the whole can of Pringles. But forgot today. So why do they call this a hyperbolic paraboloid? I think the paraboloid word makes sense because you can see parabolas in it, right? But the thing is, you can see hyperbolas in this too. The hyperbolas come from slicing that way, right? Setting z equal to a constant. And if you have a constant there, notice you have the equation of a hyperbola. And you can geometrically kind of see that hyperbola happening by asking, what would happen if you took a Pringle and took a horizontal cross-section? And I appeal to your geometric intuition. Rationalize your choice to buy a can of Pringles, right? But that horizontal cross-section is going to make what is in fact pretty believably kind of like a hyperbola. Okay. All right. So hyperbolic paraboloid. Pause for questions. How are we doing? All righty, moving along. Okay, I want to talk about various kinds of deformations of surfaces. I don't want to get rigorous about this. I just want to kind of show an example. I think the intuition, once you see an example, is really very satisfying. You'll notice a pattern, and the pattern just holds, and it's extremely believable. So here's the example. Let's consider this equation. Now, I argue that this equation here is clearly a sphere. Now, why is that clear? A couple of different ways you can see that. For one thing, this has rotational symmetry around, it's got rotational symmetry around the z-axis, but it also has rotational symmetry around the x-axis, but it also has rotational symmetry around the y-axis. It's just got every symmetry possible. And I can't think of any other surfaces that do, right? Another way you can think of this is that notice that this is the square of the distance from the origin. So basically this equation says distance to the origin equals 13. And that's clearly a sphere. Okay. All right, so that's not what we're here for. Now let me observe, quick observation, that this point here, 3, 4, 12, satisfies that equation. Kind of a little cute little curiosity. This, by the way, is an example of what they call a Pythagorean quadruple. Right? If you've heard of Pythagorean triple, like 3, 4, 5 is a Pythagorean triple, right? Because it fits in the Pythagorean. Okay. This is a Pythagorean quadruple. Anyway, so there's a point that satisfies that equation, the point on that surface. Now, I'm going to ask the question, what happens to the surface if I were to, in this equation, this is going to seem weird, but what if everywhere in this equation, everywhere I saw a z, what if I replaced it with 2z? Just, erase and trample, right? Just everywhere you see a z, put a 2z. Well, I get a new equation. This new equation, it represents, of course, a different it's a different equation, so of course it represents a different surface. What surface? When you edit the algebra in this way, what does that do to the geometry? The question I'm posing. Okay. Well, look, I make the innocent observation that this point here, right, that works in that equation, well, it sort of obviously doesn't work in that equation. Well, of course it doesn't. Right? But now let's try to break it down. Why does it not work? Well, it doesn't work because of that 2 that messes it all up. Right? It doesn't work because you can see right here, what I'm supposed to be doing is squaring that 12 that goes in there. I'm supposed to be squaring the 12, but here in this equation, that 12 that goes in there, it gets multiplied by 2 first before it then subsequently gets squared. That's not what happened in the arithmetic on the other side. Okay, so the point then is by seeing how this arithmetic fails, you can see how you can kind of reverse engineer a kind of a different point that works. And that is that, well, look, what I needed was for this to be 12, and so therefore I can make that happen by making this equal to 6. And then when you take that 6, now it's not the z-coordinate we had in the first place, but if you take that 6 and if you put it into a new equation, when you multiply it by that 2, then it becomes the 12 that you're supposed to square, and then all the arithmetic works out the same. Okay, so the moral of this story here is that this action of algebraically replacing every z in sight with 2z has the effect that it takes this sphere and it does what I'm going to call a squish, smush, squash, whatever you want to call it, right? It takes all the points that had been on the original sphere, all of their z-coordinates get cut in half, if you will. Everybody see what I mean there? Okay, the x-coordinate and y-coordinate don't change at all, though. We deliberately keep those the same. Okay, so the broader point that I want to make here, it's not about this specific substitution and this specific geometric consequence. The broader point is, and I have it written down here, whatever you do to the variable in the equation, the opposite happens to the surface. You might say the points on the surface have to be prepared to undo what you did algebraically. So now that's something that you kind of need to digest. I want you to see that rule here that I've got written down here happening in what we looked at in this first example. The points have to undo so that when the algebra does it, you're back to where you started, if you will. Okay. All right, so good general rule of thumb. So here's another example. And here I'm not going to go through the details. Not necessary, I don't think. But here's an equation that we've already understood. Z equals x squared plus y squared. Here's that surface. I ask then, what happens if in this equation, everywhere I see a z, I replace that with minus z? And I emphasize, everywhere in this equation, all of the z's get replaced with minus z's. So what happens? Well, all the points that were working in this original surface, I'm going to have to do whatever it is that undoes that minus sign. What do you do to a number to undo multiplying by -1? And well, the answer is you multiply by -1. Okay? And so that's the point of view I want to take anyway, on why you can interpret then this equation describes that surface. All the z-coordinates got multiplied by -1. Okay. All right. Here's a bunch more examples. Let's look at this equation here. What's that an equation of? Right off the bat, we don't really actually know. We've never seen that before. By the way, notice x and y do not appear in the special form. A lot of students like to say, kinda? Right? But come on. That's super cheating, right? That's not what that is. Okay, so x and y do not appear in the special form. This as I've got it written here, is not rotationally symmetric around the z-axis unless A and B are equal, hypothetically. So we can't presume anyway that it is. Probably isn't. Likewise, this is not rotationally symmetric around any axis. But what I can say is this equation kind of aesthetically looks like this equation I'll start with. Right? That equation has an easy to understand surface. That's our sphere again. We already understand that sphere. It's a sphere of radius 1 in this case. And now I just have to ask myself, what do I do? What kinds of adjustments would I have to make to turn that equation into that equation? Well, I'm going to have to turn everywhere I see an x, I'm going to have to replace that with x over a. By the way, do be very careful. Keep in mind this x squared over a squared. What that is x over a quantity squared, right? So a lot of students make the mistake of thinking, oh, well, I'm going to replace the x with x over a squared, and that's just not right, right? Because everything you put in there gets squared. So you're replacing x here with x over a. Yeah? Okay. And this action of replacing x with x over a is going to, well, let's see now. What happens when you, how do you undo dividing by a? Well, you multiply by a, right? Yeah, totally. So this action here of replacing x with x over a is going to take our sphere and it's going to stretch it by a factor of a in the x direction, right? So there's this stretching by a factor of a. And then analogously, when we replace y with y over b, well, that's going to stretch by a factor of b in the y direction. And then likewise, when I replace z with z over c, that's going to stretch by a factor of c in the z direction. And so now you got this, we've seen how to adjust good, understandable algebra into our given algebra. And so now I've got a geometric interpretation of how to take a known surface, namely a sphere, and how to do simple geometric adjustments to it to get the surface that I actually want. And so I've just got to ask, well, what happens when you take a sphere and you stretch it by different amounts in the different directions? And I think it's geometrically pretty satisfying. You get an ellipsoid. So this equation is of that surface, which is an ellipsoid. Yeah? Everybody good? Okay. All right. Etc. More examples. This, no surprise, you can see kind of a paraboloid equation kind of hiding inside of this equation that we're looking at here, and it's tempting to call it a paraboloid, but okay, well, yeah, but it is different, right? In a way in which you can persuade yourself is that this is what you get when you stretch by a factor of a in the x direction, and by a factor of b in the y direction, and by a factor of c in the z direction. So this is a stretched out paraboloid, and notice it's been stretched horizontally by different amounts in different directions. So it's not going to retain its circular characteristic, right? The fact that these two numbers here are different is what makes this an elliptical paraboloid, they call it. Its cross sections are ellipses, not circles. Everybody happy? Elliptical cylinder, right? It's the same deal. You can see the equation of a cylinder kind of, again, sort of hiding in there. You can say, okay, well, let's start with this unit cylinder along the y-axis, and let's observe. You've got to stretch it by a factor of a in the x direction and by a factor of c in the z direction. And there you go. There's your elliptical cylinder. Okay, details y'all can think through on your own. Ask me in office hours, whatever. Okay, a little word of warning. You got to be careful if there's multiple deformations happening. So, for example, let's suppose that you have this equation, and you notice quickly this looks a lot like x squared plus y squared plus z squared. All right, so we know in some sense you're going to start with this, which is a sphere, and then we're just going to start algebraically fiddling with the equation to turn it into that, and then we're going to have to correspondingly geometrically fiddle around with this to get the surface that this represents. Okay, so all right, well, be careful about the order. It's tempting to think about order of operations and think, all right, well, look, what happens to this x here? Well, clearly I'm subtracting 1 first, so I'm going to have to undo that first. And then I'm going to have to divide by 3. I'm going to have to undo the dividing by 3 next. But it ends up being that you do it in the opposite order. It seems weird at a glance, but morally speaking, the reason that things are backwards is because if you think about it, in fact, what we're doing from the start is undoing things. We are everything we're doing is intrinsically kind of sort of backwards, right? And so that leads to this little effect. And again, I just want to demonstrate by example, and I think you'll see what I'm talking about. So I'm going to first, wrong though it seems, I'm going to first replace every x that I see in this equation. Highlighter. Replace every x that I see in this equation with x over 3, thus stretching by a factor of 3 in the x direction. And it seems like I may have painted myself into a corner because aren't you supposed to do the subtraction first? Well, check it out. I'm going to now replace in this equation. I'm going to replace every x in this equation with x minus 1. That shifts by 1. The opposite of subtracting 1 is adding 1. So that shifts in the x direction by a distance of 1. And look at what I've got. I've got what I was supposed to get there. It just seems backwards. But again, everything we're doing here is backwards. So just be careful with this. Let me show you what the landmine a lot of students step on, mistake that a lot of students make along these lines is to say, okay, well, look, when I'm replacing, this thing here kind of really was the x. So, like, morally, don't you kind of have to think of that as being x or something? And the answer is, no. We've already done this, right? This equation and its surface, we're done with it. It has served its purpose. We don't need it anymore. We're not looking at it anymore. I don't really care anymore about where this expression came from or how morally I ought to think about it for like historical reasons or something. No, not at all. That's gone. Nothing above that line matters anymore, right? If you want to talk about doing a replacement, x with x minus 1, that's what it is. And forget about the other stuff that I've already scrolled up above where we can't see it. Yeah.
So I was wondering, like, a little bit more in detail, I guess, why would it not work to first shift and then stretch?
That's right. So you can do it. So that's the little comment I have down here. You could rewrite this algebra and let me zoom so we can see this better. You could rewrite the algebra if you like. Instead of thinking of it as a subtraction followed by a division, you could rewrite the algebra so that it is a division followed by a subtraction. And then, you do it the other way. You would do your translation first. And then after the translation, you would then replace, x with x over 3 and doing that stretch. And that works just fine. Now, you give me my choice, and I will notice that this involves fractions, which is a little awkward, right? I'll also notice that there was something really nice about when I did this stretch. When I did this stretch by a factor of 3 there, I did a stretch of something that was had reflective symmetry, right? And because very critically, when you stretch, you're always stretching away from x equals 0. We're stretching away from, because it's the coordinates that are getting stretched, right? So we're not stretching from the center of the object. We're stretching from the coordinate plane. And it's very convenient to have those coincide, so it's easier to draw the stretch, right? Otherwise, if you do it this way, you're stretching something that's already been shifted, and so the center moves in the stretching, and it's just weirder, right? So I encourage sticking with doing it that way and doing the stretch first and then the translation. I just think it's easier overall. It's a great question. Yeah, thank you. Okay, so heads up. Be careful with that. Okay, so moving along, we're going to talk about functions of several variables. This is, in some sense, most of the rest of the course is about. We're into chapter 13 now. We've got so chapter 12 is about setting up various kinds of tools, vectors and equations and that kind of thing. Kind of laying ourselves a multivariable groundwork of the playing field where the game is going to be played is what we've been doing in chapter 12. So here, moving on to chapter 13, we're going to see the players. Not the field. So functions of several variables. Now, I know you all have seen functions before. I just want to point out what a multivariable function is. Single variable function you all thought of before as you may have seen before. The idea is it's a box, and something goes in and something comes out. Right? A multivariable function is a generalization of in a single variable calculus class, there's usually one number that goes in and then one number that comes out. This just generalizes and says, well, what if you have several numbers going in? Several variables that are input variables for this one function. And what if perhaps you have several output variables that come out of this function? Right? Write down a bunch of examples of this in a few minutes. Talk about how this kind of thing shows up in the real world routinely. Anyway, this is what we call a multivariable function. Before I get to examples, I do want to talk about notation a little bit and sort of the way we think about these things, because it's super convenient. I make the observation that you can think of a bunch of variables as being the coordinates of a vector. Right? So this is a pretty different way of thinking about this, but instead of thinking of a multivariable function as something where a bunch of variables go in, think of it instead as something where one vector goes in. I think this is a big deal. You want to think of the inputs as being single vectors. The geometric point of view that these are vectors is going to be super useful, super valuable. Okay. And so I think it's ultimately limiting. It's very limiting to insist on thinking of the inputs as being just a bunch of numbers. We get a geometric point of view by thinking of them as vectors. We have algebraic tools involving vectors. It's a really big deal. Okay. And then likewise, the outputs. We can think of a bunch of variables as being the coordinates of a output vector. Okay. So with that in mind, here's a way we'll write it sometimes. By the way, if let's suppose there's input variables. Notice in my list here there are input variables. If you have a list of variables, that means that this, thinking of it as a vector, that is a vector in Rn. Likewise, this output, because that vector has coordinates of which there are m, can think of them as being coordinates of a vector in Rm. Okay, so we're going to think then of this function as, very often people will say, it goes from Rn to Rm. And this is a pretty nice way to think about a function. Again, it takes inputs, it gives you outputs. And this little notation I'm representing here I think it's very visually satisfying. It tells me, hey, stuff that's in here is going to get thrown over and land in here. Right? That's what a function does. Takes inputs, gives you outputs. This notation here also very common, so I would just want you all to be aware of it. All this says is we've got a function. This function's called f. And the colon here is just a way of saying, okay, all right, now heads up, this function named f, I got to tell you some stuff about it. Right? The colon says, the first thing that I list here is going to be what we call the domain. That's the world in which the inputs come from. I think I've got my prepositions wrong. The world that the inputs come from. Right? And this thing that comes after the arrow, this is the world that the outputs land in. So you'll see this notation all the time. If you see f colon rn to rm, all that's saying is, look, I've got a function. The name of this function is f. It has n input variables. It has m output variables. That's all it's saying. Okay. Little terminology. The world that inputs come from is called the domain. Very standard terminology. Think of it, if you like, you can think of it as the input space. It's the space where the inputs come from. The world that the outputs land in, it's called the target. I call it the target. It's commonly called the target. So again, you can kind of think of that as the output space. Okay, I do warn you against, there's a term that gets used sometime, the term is range. The problem with the term range is that it does mean technically different things to different people. And it's awkward. And and the difference matters. Part of the reason that this confusion about what the word range means is that a lot of people don't appreciate the significance of the difference of the two interpretations. But the difference is significant. It matters. And so as a result of people not understanding that difference, that there's just a lot of stuff out there where people are using range one way and other people are using the term range another way. And I think the term target is very clear. It's just the world that outputs have to land in. So I push for the term target because I think it hasn't been spoiled yet by misuse. Okay, so an example. Here's an easy example. Here's a function. Notice there are 3 input variables. The input variables are, as usual, listed as what we're taking f of. Here we're taking f of x and y and z. Those are the 3 inputs, which you can think of as being coordinates of a vector in R3. You can see those as inputs because, look, check it out. The output formulas are written in terms of x's, y's, and z's. I mean, they're just visibly apparent right there. The output, you can see, is a vector in R2. Why is it a vector in R2? Because it has 2 coordinates. The first coordinate is x squared minus yz. That's a formula. That's the first coordinate, right? Then there's a second coordinate, which is a different formula, which is xz. Okay, so a lot of students get confused on the outputs and think that, well, isn't this kind of like x squared minus yz plus xz? I mean, students very often just have this compulsion to add these. I don't really know why. Students are maybe familiar, just kind of so accustomed to thinking of functions as only having one output. Right? And that's not the case here. Here there are 2 separate coordinates to the output. You might say there's still a single output. It's just that output now is a vector in R2, and that single output has 2 coordinates describing it. Okay. All right. Okay. Very often we'll give the outputs names. Y'all have seen this before. Like if you have some function of x, very often people like to write y equals f of x because that f of x is a thing. I need to talk about it. Let's give it a name. Let's call it y. Right, well, likewise here, these 2 coordinates, I'm going to need to talk about these things. Let's give them names. I'll call that one V1, and I'll call this one V2. And so you can rewrite, in a sort of a familiar way, you can rewrite this equation as f of x vector equals v vector. Okay. All right. We're out of time. This is actually a pretty good place to draw the line. I'll have some real-world scenarios to talk about next time, and we'll also talk about how to visualize these multivariable functions. Okay, see y'all later. Have a good weekend.